side of the Integrating Compositions video notes. What we noticed on the front side was that if a composition integral is built correctly, we can find the integral. If it's not built correctly, then we're in trouble. There's not much we can do. So we're going to look at sort of what it is, sort of try to summarize what it is about these integrals that make them work. Right? So you can't integrate the square root of tangent of x, but you can integrate the square root of tangent x times the secant squared of x, because the derivative of the tangent of x is the secant squared of x. Right? And then let's just look at how that happens. So if we have the integral of the square root of tangent of x times the secant squared of x, which would be the same thing as the integral, just rewrite this using exponents instead, which will make it a little bit easier to work with. The antiderivative is going to be in the form of tangent of x to the 3/2 power. And in order to balance the coefficient, we're going to multiply this by 2/3. Throw a c on the end, and we're done. Example 3. We can't integrate this, but we can integrate this. Or we could integrate that. Or we could integrate anything that has any multiple of x squared. And then just as practice, let's do those. So the first one is going to be cosine of 4x cubed, and we're going to need to balance the coefficient. This will be a 1/12, and the negative is going to go out in front, so that when we take the derivative of the cosine, we don't get negative sine x, we get our positive sine x that we're looking for. This one here, again, will be cosine 4x cubed plus c. Oops, I forgot my plus c over here. Right? And because we chose the correct composite function here, or the perfect composite function here, we don't need to balance the coefficients. They're going to take care of themselves. All right? So the key idea for this, is that if you have an integral that involves a composition, right, so one function inside of another, it's really helpful, and notice we're using the word helpful here. It does not guarantee, but it is helpful if the derivative of the inside function, or some multiple of it, is present in the integral you're looking at. Right? So what you would like to have is you would like to have the derivative of this inside function be sitting right there as part of the integral. Right? And if that is the case, then integrate, oops, you can integrate the outside function, and then the chain rule is going to take care of the rest of it for you. Right? So 3 last examples, and then we're done with the notes here. You might want to turn the video off, do these 3 examples, and then come back and see whether or not you got these correct. Sometimes it's useful to rewrite these using the exponents. X to the 7th plus 2 to the negative 5th dx. And then here what we notice is that the 56x to the 6th is a form of the derivative of the inside function. So then the integral is going to be x to the 7th plus 2 raised to the negative 4th. I'm going to just carry the 56 down here. The x to the 6th is going to be the result of the chain rule here, and then I just need to balance the coefficients. So when I take the derivative of this, I'm going to end up with negative 4 out here in front. So in anticipation of that, I'm going to put a negative 1/4. When I do the chain rule and take the derivative of the inside function, I'm going to end up with a 7x to the 6th. I got my x to the 6th up here, but I have to balance the 7, so we'll put a 1/7 there, and the final answer is negative 2, and we'll get rid of the negative exponent here when we write our final answer, x to the 7th plus 2 raised to the 4th, and we remember the plus c at the end. Example 2, again, useful to rewrite the integral using negative and fractional exponents. And then this is going to be equal to tangent x. Here's my outside function. This would be 1/2. And then we notice that the derivative of tan x is indeed secant x. We're just going to need to balance the coefficient here, so we're going to put a 2 there, and we put the c on the very end. The last one, again, I'm going to rewrite this as 12 cosecant squared square root, actually hold on, we'll write this as x to the 1/2 times x to the negative 1/2 dx. And then when I take the integral of this, we're going to have, so we're going to take first the antiderivative of cosecant squared inside function. The derivative of the cotangent gives us cosecant squared. So this is cotangent of the inside function, which is the square root of x. And then the derivative of the square root of x is x to the negative 1/2. And, oh, actually, hold on, I've lost a 12 or forgotten a 12. So this 12 is coming from there. And then the last thing that I need to do is I need to balance the fact that when I'm going to take the derivative of this, it's going to end up putting a 1/2 x to the negative 1/2 in the front. So in order to balance 2 there, and we need a negative because the derivative of cotangent is negative cosecant squared. And final answer is negative 24 cotangent square root of x plus c. And we're done with today's notes.